we're going to look at the central limits theorem just to review while you guys are working on your homework here. And we're going to look at just reminders on how to use the central limits theorem from Monday in class. So the central limits theorem is basically giving us a way that we can use a set of data or a proportion or a piece of information. It's allowing us to use that data, assume a normal distribution, and then allow us to find our z-score and standardize our data through the normal steps that we've done with the normal distribution. So let's first make sure we meet all the conditions of the central limits theorem. And if you remember, the first one is that our data should be random and independent. And if you look, it very clearly says that it's randomly selected. And obviously what one mouse does does not affect the next mouse. We want to make sure that our sample size is large enough, and if you remember, we need to make sure that n times p is greater than 10 and n times 1 minus p is greater than 10, meaning that in this situation we want to make sure that the probability that they make it through is greater than 10 and the probability that they do not make it through is greater than 10. So if I'm looking at our sample size is 600, which is our n, our p is 0.78. So if I go ahead and multiply those two together, we're going to get 468, which is plenty big. We're going to do the same thing, but I'm going to do the 600 times 1 minus 0.78, and that's going to give me 132 mice. Obviously, those are both bigger than 10, so we do have a large enough sample. And then our third condition is that we have a large enough population. And if we look at this, obviously our population is all mice in existence. So obviously 600 all mice in existence is at least 10 times our sample size. So we can assume that our central limits theorem works. So we can go ahead and start working on our problem. So you can ignore this information now. That information was just to ensure that we could use our central limits theorem to find a normal distribution. So the first thing we want to do in step 1 is we want to give our normal approximation, which we all know has always been mean comma standard deviation. When we use the central limits theorem, it's going to be very similar, except we're going to use our p for our mu, and we're going to have to calculate our standard error, which will give us an approximation of a standard deviation. And how that works, basically, when we calculate a standard error, our standard error allows us to adjust our variation based on our sample size. So the larger our sample size, the smaller our error in our problem, meaning the smaller variation in our problem. It also means the smaller the standard deviation. So for this first step, let's first figure out what information we have. And they're always going to give us a p and an n, and they're always going to ask us what probability we're trying to determine. So in this situation, our p, or the proportion they give us, is 0.78, because they're already telling us that the population proportion is about 78% that can make it through. We're sampling 600 mice, and we want to know what is the probability that more than 80% of mice will make it through. So we want the probability that x is greater than 0.8. And if you remember, because we're dealing with a normal distribution, our data is continuous, so we do not have to worry about using greater than or equal to. We can just use greater than. So we can use our population proportion of 0.78 as our mean, and we're going to have to calculate our standard error to give us an approximation of our standard deviation. So to calculate standard error, we're going to plug in our p, which is 0.78. We're going to multiply it by 1 minus 0.78. And then we're going to divide it by our sample size of 600. So go ahead and do that on your calculator here real quick. And once you do that calculation, you should get a standard error of approximately 0.0169. And I'm going to use that as my standard deviation, 0.0169. Okay. Once you've calculated the standard error, now we can go through and do our problem how we have always done them. So here's our probability statement, which we need going forward, and here's our normal distribution going forward. Beyond that, I don't need to look back at any of the other information. So in step 2, I'm going to calculate my z-score, which, as we've always been taught is x minus our mean divided by our standard deviation. Okay, if you want to, you can also look at it as using the p's, but just depends on what's easier for you. If you're looking at it from the p standard, we're still using x because we're looking at our probability. We would be subtracting our population proportion, and we would be dividing by standard error. So you can look at it in either sense. So we're going to use our x, which is our within our probability. So we're going to use our 0.8 because we're trying to see what our probability of it being greater than 80% is. We're going to subtract our mean, which is our 0.78. We're going to divide it by our standard deviation, which is the 0.0169. So let's go ahead and take a minute and calculate that. Once you run through that formula, you should get approximately 1.18. And because we need to look it up in our table 2 in the back of the book, we want to leave it to 2 decimal points. So then in step 3, we're going to graph that on the normal curve. And again, our mu is going to be that 0.78. It's going to be our middle, but we don't need to worry about that. We just know that we're looking at a z-score just to the right of 1, because that's z equals 1.18. And if we go back, we notice that we're looking at the probability that we're greater than 80%. So since it's greater than, we're going to shade to the right. Okay. Then after we do that, our final step is to go to table 2 in the back of our book and look up 1.18 in your table. So I'm going to just pause for a second. Again, go ahead and take a minute and figure out what your value is from table 2. When you look this value up in the table, when you look up 1.18 in table 2, you should get a value of 0.881. And if you remember, that gives us the probability that it falls to the left. So we've got about an 88.1% chance that our data falls to the left of that line. To figure out to the right, we want to subtract from 1. And I'm just going to estimate here, we're at about 12%. Okay, so to figure it out, or to finalize our problem and make sure you do this, we would say that there is a 12% chance or probability that more than 80% of mice will make it through the maze.